Hi guys, welcome back to Data Every Day. Today we're looking at a data set of medical data from various patients, and we're going to try to predict whether a given patient has heart disease or not. So this last column here is 1 or 0, 1 being heart disease, 0 being no heart disease, and we're going to try to predict this column using all the others. You can see we have a bit of information about each feature, and many of these, in fact all of them, are already encoded in numerical form. Some of them will be just pure numerical data, and then others will be some nominal features such as this, where we have different categories. And then I think there are some ordinal features as well, like this one, this resting ECG results. Actually goes in ascending order. So let's hop into the notebook. I'm going to use NumPy and Pandas to work with the data, and then we're going to do some visualization with PyPlot and Seaborn. Just setting the style for Seaborn there. And then we're going to use the standard scaler, min-max scaler, and robust scaler, and the train test split function from sklearn for pre-processing. And then our models today, we're going to use logistic regression, support vector classifier, and MLP classifier. So I'll go ahead and import those, and I will load in the data using pandas.readcsv. And we can grab the file path for the CSV file over here and paste it in and take a look. So we have 14 columns and 303 rows. So like I said, everything is already in numerical form. Let's just get a little information about the dataset with data.info. And we can see there's actually no missing values here. 303 non-nulls in each column, and you can see there's 303 total entries, so therefore 0 null in each column. And then additionally we have all numeric data, everything being integers, and then a single float column for the old peak, which if we look back here, old peak is ST, actually I'm not sure what ST is. ST depression induced by exercise relative to rest. So I'm not actually sure what ST is, but it says old peak, so I'm guessing this is some sort of peak of some sort. It's not essential that we know what it is, because we know it's a numerical column, so there's no worry about how to encode it. However, there are some in here, like slope, THAL, where they are actually categorical features, and so we're going to have to encode them in the proper ways. So what I'm going to do is start pre-processing here. I'm going to create a function called preprocess inputs, and basically preprocess inputs is going to take in the data frame. We can start by creating a copy of it, and then we're going to return x and y after it's been fully processed. So y is going to be what we're predicting, which is the target column. So df sub target is going to be y, and let's just make a copy of it. And then x is going to be everything except the target column. X is what we're using to try to predict y. So we'll drop it from axis 1 and make a copy as well. And if we just have it like this, you can get x, y from preprocess inputs, and I'm going to pass in data as the df. Now we can take a look at x and y, and all it is right now is the original data set, but with the target column separated from the rest. So now what I can do is go in here and start and add all my pre-processing into this function, and x will change, and we can keep viewing the results as we go. So let me just comment this, split df into x and y, and let's think what the first thing could be for x. Well, we know that there are no missing values, so we don't have to worry about that. So I guess all we have to really do is encode the data. So what I mean by encode is, let's take THAL as an example. It says very clearly here that THAL is a nominal feature. In other words, it's a categorical feature whose values do not take any specific ordering. So you can't really say that fixed defect is less than reversible defect. You may try to. You could encode it as an ordinal feature and leave it as it is, or switch the values around. But that's going to bring the model to believe that it sort of takes on an order, which can actually hurt the performance of the model. For such a column, it's best to use one-hot encoding, so that each unique value gets its own column. And you can see what that would look like here with pandas.getDummies. This is a function that can get you one-hot columns based on a column. So let's pass in the THAL column, and you can see each unique value in THAL gets its own new column, and it's a given value for a column is given by a 1 or a 0 depending on what the original value was for that example. So for example, I'll show you example 0 had a THAL value of 1. So for example 0 in the dummies, we have a 1 for the 1 column and zeros in all the others. Similarly, we had a 2 and 2 down here, so we have a 1 and a 1 in the 2 column for these examples. And yeah, so we're going to apply this kind of encoding scheme to all the categorical features. So I'm going, not all of them actually, just the nominal ones. Nominal meaning there's no ordering between the columns. So we'll say one-hot encode the nominal features. And I'm just going to make a list of the nominal features here. So it's going to be, if we look into here, we can sort of get it. The chest pane type, this is also a nominal feature, because there's no ordering necessarily between the different types of chest pane. So we're putting CP in there. Then we have, well, this is clearly not a nominal feature, this is just numeric. Cholesterol also numeric. FBS, let's look what that is. Fasting blood sugar. This is actually a binary feature that's saying if the fasting blood sugar is over 120 milligrams per DL. I'm not sure what DL is. I'm no medical expert. But it's basically a yes-no column. And with a yes-no column, there's no need to encode. It's already in a suitable format, either 1 or 0. In fact, this just looking at this head, or this the first 5 and the last 5 rows of the data isn't actually good enough for understanding what kind of data is held in each column. So what I'm going to do here is create a dictionary that's going to map a column name to the length of unique values in that column. So essentially, we're going to map each column name to how many distinct values are in each one. That's for every column in x.columns. And we can see age has 41, that's because it's numerical. So sex has 2, so it's binary, no need to encode. CP has 4, and they're not in any order, so that is going to be nominal, so I'm putting it up here in this list. T rest BPS is not as numerical, so no encoding. Cholesterol also numerical. FBS, this is binary, so no need. Rest ECG, so this one is categorical. It either takes a value of 0, 1, or 2, and we could encode it in a one-hot encoding, but I was actually experimenting with this dataset earlier, and it seems that the model performs better when this is treated as an ordinal variable, so left as it is. That would suggest that this truly is an ordinal variable, and there's more information captured by keeping it in an ordinal format. We actually lost a few percentage points on our accuracy when we tried to treat it as a one-hot, as a nominal feature. Okay, THAL ACH, this is a numerical variable, so no need to encode. And then XANG is binary, no need to encode. Old peak, also numerical. Slope. Slope is the slope of the peak exercise ST segment. So I'm not sure exactly what it is, but it has 3 different possible values, 0, 1, or 2. And this actually is nominal. And the reason I say that is only because I was experimenting, and the model performs best when it's treated as a nominal column. So sometimes you actually just, if you're not sure, if it's not clear in the description of the data, it's best to try it out with different encoding schemes and find what works best. So it's best to treat slope as nominal. CA has 5 different values, and you can see this is the number of major vessels. At least I think it is. I assume these match up, and there is no other description of it, even though this says 0 to 3 and this one has 5 possible values, but it is best treated as ordinal as well. So THAL at the end, that's also going to be nominal. It says here very clearly that there's different possible values, and this one only lists we have 3, 6, or 7, but there's actually 4 possible values in the real data set, so I'm not sure what that's about. But again, the model performs best when this is included as a one-hot column. Alright, so this is all we're going to do. We're going to encode these ones. And I'd like to just take a moment and come back to this in a second, because I'd like to just visualize a bit of the data. So we're going to do a little EDA, Exploratory Data Analysis, and we're going to, here, I'll just mark this down a little. Let's get some box plots for each numeric variable, and a correlation heat map for the dataset. So I'd like to just list out the numeric features, because I only really want to visualize what's going on with the numeric ones. It's a bit misleading to get box plots for categorical features, because outliers aren't really outliers. Also for correlation, since there's only a distinct number of values a categorical feature can take on, it doesn't really make sense, especially for the nominal features, to show greater than or less than in the correlations. Am I making sense? I think it's best to use numeric features for this kind of visualization. So I'm just going to get a list of them. I'm not going to type it all out, just paste it in. These are the numeric ones. I took out these 3, and then also I took out the ordinal features. So we're just left with the numerics. And then I'm going to create a separate data frame called EDADF. This is just what we'll use to explore the data a little. That's just going to be data.loc, which will slice the dataset, targeting all rows and just the numeric features as columns. And I'll make a copy, and that's going to be the one we're using now, just for exploring. So I'm going to create a new figure. Fig size, do 16 by 10. This is going to be a grid of box plots for each variable. And since there are, I believe, 8 different numeric features, we're going to create subplots in a 2 by 4 grid. And what we'll do is, for I in range length of EDADF.columns, so we're saying for each column indexed by I, we're going to create a subplot in a 2 by 4 grid indexed by I plus 1, and that's because subplot indexing has to start at 1. We'll create, for each one, we'll create a box plot with SNS.boxplot, and we're going to get the box plot for a given column. So EDADF, and the column we're passing in is going to be EDADF.column sub I, so the ith column. And then we will show the plot after all the subplots are generated. Alright, so we can see for each variable we have a box plot that shows, for example, in this one, this blue box represents the different quartiles. This is the first quartile, the second quartile or median, and the third quartile. And then these lines on the side represent So the distance from this, for example, for this one, the distance from the second quartile to the first quartile times 1.5 and then subtracted from the median. That's it's a good way of visualizing where outliers appear, because data that lies outside of 1.5 times the interquartile range is generally, it's very far from the bulk of the data. So you could consider these as outliers, and that's why they're represented as dots. You can see we have some potential outliers here, especially this one, because it's so far from the, like there's nothing in between. This might actually be a dangerous outlier. So we could remove it manually. Another thing we can do is use a robust scaler when we scale the data, which is robust to outliers, and we'll scale it with outliers taken into account. And then another thing I just like to visualize here would be the correlations. So I'm going to create a correlation matrix from the EDADF, so just the numerical features. I'm going to get that with .core, which is a pandas function. And then we'll create a new matplotlib figure. Fig size here can be 12 by 10. And it's going to have a seaborne heat map passing in the correlation matrix I generated. I'm going to turn on annotations. I'm also going to set the minimum value to -1, since that's the lowest possible value of a Pearson correlation. And then turn on the C map. This is just a color map to make it look nice. Or Mako. Okay. I'm also going to just give it a title. Correlation heat map. And we'll show it. plt.show. Alright, here are the correlations for just the numeric variables. And you can see we don't really have any really powerful correlations. The strongest one here looks like this one, which is between slope and old peak, a negative correlation of 0.58. And that's still not very substantial. It looks like our strongest positive correlation will be this 0.39 here. But nothing too worrisome. And honestly, even if we had some really high correlations here, we don't have too many features and we don't have a lot of data. Even if we had extremely high correlations, it'd probably be best to keep all the columns in here, because we don't really have much risk of overfitting by having too many columns. I guess what we can also do is visualize the class distribution. So I'll say we can also visualize the class distribution with a pie chart. So we'll just create a new figure really quickly. This can be size 8 by 8. And it will be plt.py, and we're going to pass in, we want the class distribution, so EDADF does not include the classes. I'm going to do data subtarget to get the classes, and we don't only want the target because, well, we want the value counts of the target. Value counts is basically a pandas function that takes a column and looks at the unique values in the column and then how many of each unique value there are. And so we're creating a pie chart from that data, and then we're going to give it labels. The labels should match up with the first occurrence, second occurrence in the value counts. So the 1 is heart disease, so the first label will be heart disease, and then the 0 is no heart disease. Alright, and then we'll also include some colors just to keep it consistent with what we had. Actually, before colors, we're going to turn on auto %, which is just going to display some percentages on the pie chart for us. And we'll format it with a 1 decimal place, and then a % sign after. And then the colors we're using here are going to be, I already extracted them from the correlation matrix, it's just to keep it consistent. Alright, and then we'll show. We can also give it a title, class distribution. Alright, here it is. You can see 54.5% of the data is positive and 45.5% is negative. So, I mean, this is enough. We could go further. We could also visualize like the distribution of male and female patients. We could show the age histogram or something else. There's endless possibilities for exploratory data analysis. But I'm just going to get back to working pre-processing, one-hot encoding, and then we will train. So we haven't actually one-hot encoded yet. I'm going to create a function called one-hot encode. That's going to take in a data frame and a column dict. So this column dict is going to match up column names that we want to encode with the prefixes to use in the dummies. So remember, from like I said, we can use pandas.getDummies to take a given variable, actually on x, and then we can also include here a prefix. How about th for thal? That will just append this little prefix to the beginning of the column names so that we know where each one-hot column originally came from. So down here, what I'm going to do is I'm going to iterate through, well actually first let me just make a copy of data frame. And then for each column prefix pair in column dict.items, so this is going to be a dictionary that matches a column to a prefix, and we can use .items to return the pairs as tuples, which we can then iterate through two at a time with column prefix. And we're going to create some dummies for each pair of column and prefix using pandas.getDummies like we did above, passing in df subcolumn and setting the prefix equal to prefix, which we're passing in here just like this, right? And then df is now going to be pandas.concat, which will concatenate two data frames. We're going to concatenate the original data frame and these new dummies columns side by side, so on axis 1. And when we're done, all we're going to do is drop the original column from which we created the dummies. Alright, and then we'll return df, and that will be it. This is all we need. Now we just have to create a column dict. So we can say df equals one-hot encode. That's our function. It takes in a data frame, which is just itself, and then a column dictionary. So note that if we grab a list, so let's actually just call it nominal features. Note that we can use the zip function to zip two lists together. So if we grab a list and we zip it with another list, this can be a list of prefixes. So CP, SL, and TH, and that will just return a zip object, but we can display it as a list to show to group them up element by element into tuples like this, so they get paired up. We can also display it as a dictionary, which will instead map them in key value pairs, right? So this is what we want down here. Note that this is given by nominal features, so we can just replace this list with nominal features and we'll get the same thing that will match the list of nominal features with the corresponding prefixes for each column. So down here what I'm going to do is pass in similar to what we have here, dict zip. Actually it's this exact thing. We're just going to pass that in here. That's going to be our column dict that we're passing in here, that is going to extract the column and prefix from column by column, and then generate the dummies, append them, and remove the original column. So now let's take a look what that does. This is what we had before. We have our nominal features, which are CP, slope, and THAL. Now if we take a look at X, we now have these new one-hot features here, which are 1s and 0s, and you'll see the original columns are gone. So that's all we have to do for preprocessing. We also should scale the data. So scaling ensures that every column takes on a similar range of values. Right now they're all over the place. These columns only take values between 0 and 1, whereas over here we have values that go all the way up to 200s. So we want to ensure that each column takes the same range of values. So what we're going to do here is scale x. So we want to try this out with different scalars. So I'm going to pass in a scalar along with the data frame, to our preprocess inputs function. And what we're going to do is set x equal to scalar.fitTransform. So these scalars that I'm going to pass in are from sklearn, and they all implement a fitTransform function that takes in some data and then will apply the proper scaling scheme to each column. And those always actually return a NumPy array, so I'm going to turn it back into a data frame afterwards, keeping the column names the same as they were before. And so that works. Now we just have to pass in a scalar. I imported 3 scalars at the top: a standard scalar, a min-max scalar, and a robust scalar. Like I said, I'll just give you an example. I'll tell you what each one does. Standard scalar will give each column a mean of 0 and a variance of 1. So most of the values in each column will lie between -1 and 1. The min-max scalar will squish the range of possible values to between 0 and 1 so that the minimum lies at 0 and the maximum lies at 1. And then the robust scalar is very similar to the standard scalar, but it's robust to outliers, so I believe it shrinks outliers in more than the other data. So like this one will be pushed in a little bit more. And then, so we're going to pass in each of these scalars and see how it affects the performance of our model. So we'll start with a standard scalar, creating a new instance of it and passing it in. And so now if we take a look at x, you can see each column has been scaled so that it has a mean 0 and unit variance. Note that if I did this with a robust scalar, it looks very similar. Actually interesting to see that these ones were not scaled with the, No, I'm not entirely sure how the robust scalar works. I'll take a closer look. But if you want to go check it out, I think sklearn has some documentation on it. However, I do know that it takes into account outliers when it performs the scaling. And the min-max scalar last will shift each column to have a maximum of 1 and a minimum of 0, like I said. So we'll try it with each. We'll just keep it as standard right now. And then we don't need this anymore, but we are going to now start training. So first thing to do when training, we're going to create a train set and test set of our data using the train test split function from sklearn, which I imported earlier. And we're going to pass in x and y, and it's going to split them. It's actually going to shuffle them. It's going to shuffle the data and then split it with the train size that we specify. So we'll take 80% of the data for training, since we don't have that much data. And then we'll give it a random state, 0. This can be anything. This is just to ensure that the shuffle and the split is always done the same way. And so this is going to generate 4 new sets of data: xtrain, xtest, ytrain, and ytest. And now we can train on the train set and test the results of the model on the test set. So we'll create 3 models: logistic regression model. We'll have a SVM model. This will be our support vector classifier. And a neural network model. This will be the MLP classifier. So for each one, we're going to fit our model.fit on the train set, xtrain, ytrain. And we'll do the same thing for here and for here, this one being SVM model, and this is NN model. And when we're done, we'll print out the results. So logistic regression accuracy. We'll display it to 2 decimal places and format the string with lrmodel.score on the test set. So we're getting the accuracy on the test set. And we'll get a percent sign and multiply it by 100 so we can get it as a percentage. And we'll do the same thing down here, but this will be support vector machine. And this will be the SVM model. And down here as well, but this will be neural network and NN model. Alright, let's compare the results. So we ended up with a logistic regression accuracy of 85.25%, a support vector machine accuracy of 86.89%, and a neural network accuracy of 88.52%. So it looks like the winner is the neural network, support vector machine in second, and the logistic regression model in last. But let's try it with some other scalars. So all we have to do to change the scalar is switch this. We'll try it with the min-max. So run this again, run this, and then we're going to check logistic regression, and that looks like an increase about 1%. This is an increase of about 2%, and this is an increase of about 2% as well. So it looks like the min-max actually is a better scale for this data. Last one I want to try is the robust scalar. As we saw earlier, we have some outliers here, so maybe the robust scalar will give us some of the best results here. Scaling, and then making our split and checking the results. So no change here, no change here, and there is actually a negative change here. Oh, but there is some stochasticity here. It's actually shifting around. But we seem to be getting, I don't know, neural network is giving us the best results, but it's also the least consistent. If we run these should be the same almost every time. But the neural network, the results change after each run. So it's hard to say which is the winner. What we could probably, the neural network probably wins, but we have to make sure that I think in practice we would want a larger test set to train on, because if we look at this test set, if we look at how many examples we have here, there's actually only 61 examples that we're calculating this percentage on, so not so big, right? And additionally, the actual the percentage of this can actually really affect the accuracy. For example, if I lower this to 70% of the train size, these should all go down by about a few percentage points at least. So when you have such few rows, the model accuracy is very sensitive to like what portion of the data set it was used to train, and also how large is the test set that we're training on. But all in all, I think it was a pretty successful fit. We're getting pretty high accuracies in each one. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.